Now this is the sizes or the formulas which are given in decimal. Now how to get the address in binary? So this is somewhat difficult, and okay, I want you to pay full attention here. Whatever I am going to teach you is not that easy to understand. I'll try to make it as simple as possible, but then you please focus on this, okay? So writing the addresses in binary and decimal is straightforward, but when I try to convert the same addresses into binary, then it is going to be a bit tough in a sense, okay? So let's talk about this. What is the address of a particular element ij in when the indices are starting from zeros? So most of the cases our computers are going to have indices starting from zeros, because the main memory is also starting with zeros, so it is natural to have indices starting from zeros. So I am going to take here, assume that the indices are starting with 0, then what is this? See, in order to get into a of ij, right, where a is a m by n array, if the indices are starting with 0, then I told you that it is I into n plus j into s, where s is size of the element and plus base is anyway there, okay? So this is the formula. Fine. Now I want to write this entire address in binary. That is what I want to get, okay? Then now one thing you should understand is, in computer science generally everything will be in the power of 2. So even let us assume that even the array sizes are also given in powers of 2. In case if the array size is also a power of 2, okay, what is n here? N is the number of columns, remember? So A is an m by n array, which means n is the number of columns. Let us say, then what is the relationship between j and n? If n is the number of columns, you can clearly understand one thing. The relationship between j and n is 0 is less than or equal to j is less than or equal to n minus 1, which means j will be definitely less than n, right? So the relationship between j and n is j will be less than n, right? Now assume that n is a power of 2 and assume that n is 2 power k, right? What does it mean? The number of columns we have is equal to 2 power k. Are you following it? The number of columns we have is 2 power k, right? And then now if j is a number less than 2 power k, okay, see, j is a number less than n, and I am assuming that n is a power of 2, and if j is a number less than 2 power k, then how many bits will be required in order to represent j? The number of bits that will be required to represent j will be definitely less than or equal to k, isn't it? If any number is less than, if any number j is less than n and n equal to 2 power k, what does it implies? This implies that j is less than 2 power k, right? Now what does it mean? In order to represent j in binary, we need less than or equal to k number of bits, isn't it? The number of bits which are used to represent j will be less than or equal to k. Keep that in mind, okay? Now, and you can even assume that the number of rows m is some 2 power l, right? Then what happens? Then I is also less than 2 power l, therefore the number of bits required to represent I will be l, right? So now you can write it like this: I into 2 power k plus j, isn't it, into, you can even assume that size of this size of the element is also a power of 2. Let us say 2 power x plus base. I am writing everything in 2 parts, right? Now what you could do is, you could represent this I in binary. Let us say I have represented this I in binary. This is the number I, right? And when I multiply any number with 2 power k in binary, it is nothing but adding k zeros, isn't it? Appending k zeros. So these are nothing but k zeros, which is nothing but I multiplied with 2 power k. And when I add j, right, I am going to add j here, isn't it? And you already know that j is going to take less than or equal to k bits, right? Therefore this entire representation can be represented using I can be represented in l bits and j can be represented in k bits. So the total number represented is l bits plus k bits, and then multiply with 2 power x. Therefore x bits will be here. I don't know whether you understood this or not. Okay, I'll even take a numerical example and explain you, but anyway, just try to focus here one more time. See, what is that I'm trying to say is, okay, maybe I'll do it again. This is not very simple concept to follow, but then let's go step by step. Maybe you might understand it then. Okay, so I'm talking about row major order. So in row major order, I'm talking about Aij. You already know that in order to reach Aij, I have to cross I rows, right? So if I have to cross I rows, then how many elements I should cross? Number of columns. I into number of columns is n. These many elements I should cross in order to reach the particular row, and after reaching particular row, I should cross j elements in order to reach that particular element, right? So this is the total number of elements I should be crossing, and if the size of each element is s in terms of words, this is the total number of words I should be crossing to reach the element Aij, and base is b. Got it? Now I want to find out the address, right? So what is that I am trying to do is, now I am assuming that m is 2 power l and n is 2 power k, which means the dimensions are, I am assuming that in the dimensions are represented using powers of 2 without loss of generality, right? And now what about I? The I is nothing but the row number. Row number will generally vary from, if you assume that it is starting with zeros, the row number, which means I, will vary from less than or equal to 2 power l minus 1, isn't it? And what about column number? The column number will also be less than or equal to 2 power k minus 1. 2 power k minus 1. So what do you understand? Either in order to represent I or to represent j, the number of bits required will be less than or equal to l, isn't it? See, what is the maximum number that could be represented using l bits? 2 power l minus 1, isn't it? What is the maximum number that can be represented using 2 bits? 3. What is the maximum number that could be represented using 3 bits? 7, right? 4 bits? 15. So 2 power l minus 1 is the maximum number that could be represented using l bits, right? Therefore, if you are never crossing the maximum number which could be represented using l bits, then how many bits are used to represent the number I? In worst case, l bits, right? Therefore, you can represent any number I if its range is 0 to 2 power l minus 1 using l bits. So l bits are enough to represent I. What about j? K bits are enough to represent j, isn't it? Now I'll write this entire address like this. The entire address can be written like this: I into 2 power, what is n? K, plus what is j? Let me leave it as j, and let me say the size of the each byte, size of each element is 2 power x words, right? Then it is 2 power x plus b. Got it? So this is the number of words for each element, right? And now see, how many bits are used to represent I in binary? L bits. So L bits are enough. So using L bits, I can represent I. So I is represented using L bits, right? And now when I is multiplied with 2 power k, right, then what does it mean? Whenever any binary number is multiplied with 2 power k, it is nothing but left shifting this number those many k times, right? Therefore, I into 2 power k is nothing but appending it with k bits, and all k bits are zeros, right? So I is nothing but L bits, and L bits I is represented, and this entire number is this one. And now I have to add j, right? So what is adding j? Adding j is nothing but convert j into a binary number. How many bits are required to convert j into binary number? K bits, right? Therefore, you can get j which is represented in k bits, and you can add it, right? Therefore, now this entire number is actually represented using k plus l bits, isn't it? So now this entire number is going to be represented using, here there are L bits and here there are k bits, right? And what is this? This is I and this is j. So I is nothing but the first index, isn't it? I is nothing but the row number, and this is nothing but the column number, isn't it? See, if aij is given, I is nothing but the row number and j is nothing but the column number. So you can represent row number here and column number here using the L and K, right? And we got this entire number in how many bits? The number of bits required is L plus K bits, right? And then you have to finally multiply with 2 power x. So what is multiplying with 2 power x? Appending x number of zeros. Got it? So this is the entire address of this element in our in binary, right? And finally, anyway, you have one more binary number which is base. You convert this base into binary and you can add it, right? Anyway, that doesn't make any difference. So only important part is this. So what did you understand from this? In order to represent any, in order to get any address, right, you have to do this. You have to take the take the address, and then the least significant x bits is going to be the size of the element. If the size of the element is 4, it is going to be 2 zeros. If the size of the element is 8, it is going to be 3 zeros. And then in case of row major order, here it is going to be column number and here it is going to be the row number, right? Depending on how many ever bits you want to represent row and column, right? So this is how the address can be found out in case of row major order. What happens in column major order? The same thing, right? In column major order, same thing. You have to have this x number x, where x is the size of the 2 power x is the size of each element, and then here you should have row and here you should have column. So why do you think that this way it is followed in row major order and column major order is, in row major order we have to cross first rows, we have to cross first the rows, and then after crossing the rows you are supposed to go into this after crossing the rows, you are supposed to get into the row which is required, and you have to cross the elements to get to that element, right? That is why row number is here and column number is here. By writing row number here, this will make sure that you are going to cross all the rows before you get into the desired row, and after getting into the desired row, you have to cross these many elements, right? See, row and column doesn't mean that you have to put the number of rows and number of columns. Row and column means that what is the first index and what is the second index. In case of column major order, you are supposed to cross the columns. That is why the second index here and then the first index here, right? So which means, see this, instead of putting a row column and column row, if you are getting confused, you can even put like this. So if a of ij is required, what I mean to say is, this one is the first one, this one is the second one, right? So in case of row major order, put the first one here and the second one here. In place of column major order here, put the first one here, put the second one here, and then the first one here, right? This can be extended even to 3 dimensions. In case if you have 3-dimensional array, put the first one here, second one here, third one here, and finally the size of the element, right? So it can be extended to any number, right? Fine. And so this is how you can think of the array elements, right? So this is all about the row major representation and column major representation. So one thing is, why is this important that you should understand all these concepts is, depending on the way in which you have written your program, or depending on the way in which the memory is organized in the 2-dimensional array is organized in the main memory, you can write the programs in such a way that they will take the advantage of this organization. See, in case if you think that row major order is used, then what happens? This entire part will be placed together, and then this entire part will be placed together, and then this entire part will be placed together, right? And then let us say the entire part happens to fall in, if this is the organization, then what happens is, in terms of paging, the entire row might fall in one page, right? Then if you try to load one element, or if you try to access one element, you will get all these elements in that page. Therefore, you can write your program in such a way that it will take advantage of this organization, and immediately when you get one element, you can try to access all the elements without any page fault. So in case of row major order, accessing the elements row by row is going to give you less number of page faults. In place of column measure order, accessing the elements column by column is going to give less number of page faults. Why? Because whenever you try to load one element, in case of row measure order, the entire row will be loaded in one page. Therefore, if you try to access them row by row, only for the first element there will be page fault, and for all the remaining elements there will be no page fault. Got it? So whatever the memory organization is, you could still write some kind of program which will take the best advantage of it and give the best performance. But then once the program is fixed, which means once you have written the program and once it is fixed, then the performance of the program depends on what kind of organization they have used. In case if they have used row measure order, then the performance will be in one thing. In case of they have changed it to column measure order, the performance will change, right? Therefore, knowing the organization well ahead and then writing the program will give you better performance than writing the program and then asking it to adapt to the organization. Are you getting this? See, what I am trying to say is, in case of paging, if it is row measure order, there are chances that one row will fall in one page. Therefore, when you get the first element, you access all the elements of that row only. In case of column measure order, then there are chances that one column will fall in one page. Therefore, when you get the page for the first reference, then you try to access all the elements of the first column. Are you understanding it? The same thing can be applied even for cache also. In case of blocks, and whenever you are using this row measure order, whenever you load one block, there are chances that the corresponding elements which are in the entire row will be loaded. Therefore, you write the program in such a way that it will access all the elements row wise, not the column wise. See, if you are using row measure order and if you are accessing the elements in the column wise, what happens is, whenever you load any program, whenever you load any word, then the entire row will be loaded, then immediately you will be asking for the next column instead of asking the next element in the row. That is why, depending on the organization of the two-dimensional array, either row measure order or column measure order, you choose the program, but not the other way around, which means you don't write the program and then you don't think that it will give the same performance in all kinds of organizations. Got it? So what I mean to say is, either it is row measure order or column measure order, you could still write the programs in such a way that it will run efficiently, but then only for one order. Let us say the given organization is row measure order, then I'll write the program in such a way that I'll try to access the elements row wise, then that will give the best performance. If the program is column measure order, then I'll try to write the program in such a way that the elements are accessed column wise, then that will give the best performance, right? So once you have fixed up the organization, either row measure order or column measure order, then it is up to you to write the correct program. Got it? Okay, we shall see some questions on that, you will understand it better. So especially in CO, we shall see how to combine the arrays, the concept of two-dimensional arrays and the memory organization along with the blocks. Then you will understand what is really going on. Okay, fine.